In class, we should have gotten down to the point where we established the fact that an LTI system is asymptotically stable if and only if the poles, all the poles of the transfer function have negative real part. And so that means that the stability of the system represented by the transfer function y of s is determined exclusively by this denominator. And in particular, it's the roots of this denominator, or the things that make it zero, the values of s that make it zero. And so oftentimes what we're going to want to do is factor this into different s plus something, p1 times s plus p2, and so on. But sometimes that gets a little nasty, especially when n gets relatively large. And so it's interesting to understand when, just looking at the denominator in this form, we can determine that all the poles are stable. So all of them have negative real part. And so we're going to build up a tool here that allows us to do this. One thing to note before we launch into that is that we can, if we do have an expression like this, where all the poles essentially are negative, so if all the pi's, all these poles are positive, then that means the s that makes that negative is in this case, negative p1 makes this term 0. And so the pole is minus p1. So in this case, we know that all of the poles are stable. And if I multiply this out, this shows me that all of these signs should be positive. And that's simply just because all I have are positive values. And once I expand all of this, I'm still going to have positive values where these alphas are all positive as well. And so a necessary condition is that all the coefficients in the denominator need to have the same sign, because you can always factor out a minus sign. So if they're all minus or they're all positive, then you can say that it's possible that all the poles are stable. What we're going to see is that it's possible to have all positive values in this denominator and all these alphas are all positive, but it's still not a stable system. So in that case where we need to dig a little bit deeper, we use the Routh stability criterion in order to determine the stability. And this is actually a result from long, long ago, 1870s in fact. And so it's really a mathematical result that's been ported into an engineering application. It's really about knowing how, whether or not the zeros of a polynomial are positive or negative. And so we've ported that for our purpose here because we need to understand the stability through the zeros of the denominator. And so what this is going to boil down to is we're going to compose the Routh array, which is essentially a big table with some rules about how to construct it. And if all of the elements in the first column of this table are all positive, not zero and not negative, but positive, this means that all the poles are stable. It may feel a little bit old school and clunky. However, one of the cool things that we can use this for is for design of controllers. And this will be something that we consider in the future towards the end of the class, where we're now going to introduce a controller into the system, and we're going to want to know when it's stable. And so we can use the Routh criteria to establish that. So this is a general, feels like an example, but this is actually the general case. So if I have a transfer function g of s and the denominator, remember that's what determines the stability, is given in this general format where the alphas, the first term is 1, the coefficient is 1. So if that's not 1, you have to divide by that value to make sure that this coefficient is 1. And then all of these coefficients multiply the different factors of s. And so notice the first check is to make sure that all of these alpha are greater than 0. If they're not, then you can automatically say that there's at least one pole that's not not stable. But if they're all positive, then the next step is to build the Routh array, which confirms whether or not the system is stable. And so the way that you form the Routh array is you put down in the first row, you put down all of the even coefficients. So you start with this 1, then you add alpha 2, then you'd add alpha 4, alpha 6, and so on until you reached the end of the even elements. And then in the second row, you put down the odd coefficients. So you'd start with alpha 1, then put in alpha 3, and then alpha 5, and so on until you run out of odd coefficients. So the first two lines are established based on directly from your denominator polynomial, and then the rest of the lines are constructed using this set of rules. So for all of the b values in the third row, effectively notice that the denominator is going to always be the same, and it's this value alpha 1. And so for b1, we calculate b1 by multiplying alpha 1 times alpha 2 and then subtracting 1 times alpha 3. And then we put that over the denominator alpha 1. To calculate b2, we do the exact same process, but we do that with the first and the third column. So in this case, we take alpha 1 and multiply it by alpha 4, and then subtract 1 times alpha 5, and still put it over the denominator alpha 1. The same works for b3 if we had alpha 6 and alpha 7 out here. We would use them to calculate b3. And what's going to happen is that if you don't have this alpha 6 and alpha 7, those terms will be 0, and so that will start to introduce zeros into the right side of the Routh array, kind of like down here, where eventually you're going to reach a point where you're just going to have one entry, and then the next entry below that would be 0. So the C terms, then the fourth row here, follows in the same pattern, where now we're going to consider, again, the first and the second column, but now the common denominator is going to be B1. So it's like we're shifting everything down by one row when we move from the third row to the fourth row. So to calculate C1, we take B1 times alpha 3 and subtract away alpha 1 times B2 and put it over B1. For C2, we do the same thing, where we now use the first and the third columns. We multiply B1 and alpha 5 and subtract away alpha 1 times B3, and then again put it over B1. So this is simply just rules, and it may take a few tries to remember exactly the order, but it's very systematic, and eventually you'll start to get these zeros, and that will lead to essentially a final element down here where the next one would be 0. And that's when you stop. And then what you do is you look in this first column, and you're looking for changes of sign. And because this first element is 1, anything that changes from positive to 0 or positive to negative is going to indicate a unstable pole. And you can actually say further that the number of sign changes that this first column shows is equal to the number of poles that have a positive real part. So let's take an example. Here I have my transfer function, and this is the denominator that we care about. And remember, it's only the denominator that determines the stability. And the first check is that all of these coefficients are all positive. And so that means that it could be that it is stable, but now we'll have to build the Routh array. If one of those was negative, or if multiple of those were negative, such that there were different signs exhibited in the denominator, then that would mean automatically that this transfer function is unstable. So we build out the Routh array because we need to know further information. So we put down the even coefficients. The first one is 1, then 3, and then 5, and that's the last one, so we stop there. The even powers, the even coefficients are 2, and then 4, and then we run out, so I'm going to put a 0 here. And now we compute the different terms of the Routh array. And so the first element is computed by 2 times 3 minus 1 times 4, and then put it over 2. And then the next term is given by the first and the third columns, which is 2 times 5 minus 1 times 0. And so this is an example where this 1 times 0 here becomes 0, and now this cancels with this, and you're just left with a 5, which is this original number up here. And so that's how you start introducing further zeros here, then here, and then now here into the Routh array. On the next line, we do the same kind of process where we take the first and second columns. So we take 1 times 4 and subtract 2 times 5, and then put it over 1, and that's minus 6. And you continue this process, and what you get is this Routh table. So you may pause the video and finish it off if you want to. And so you get this Routh array, and what this says is this term is positive, this is positive, this is positive, and then this switches to negative. So right here is the first sign change. And then it switches back to positive to get to the 5. And so this is the second sign change. And so because there are 2 sign changes here, that says that G of S has 2 poles with positive real part. And that's all there is to the Routh stability criterion. And again, later we'll use it for assessing stability based on different parameters that we may introduce because of controllers or other factors of our dynamical systems.